All right, so let's take a look now at section 5.4. We're talking about systems of nonlinear equations in two variables. Now, when we saw systems of linear equations in two variables, we saw two methods that we could use to solve, the addition method and the substitution method. And we saw that both of them are reasonably useful in that context. For nonlinear systems of equations, we're going to notice that although the addition method is sometimes possible, more often than not, the substitution method is the one we're going to go with. So let's start with an example. And here, even though we're dealing with nonlinear systems, the directions haven't changed. We're still going to solve the system. The first system we're going to start off with is going to be 4xy. Notice that's not linear anymore. Plus 3y squared is equal to -9. And here 2xy plus y squared is equal to -5. So now here what we want to do is we want to eliminate one of these by adding the equations together. We can either choose to eliminate this or this. Now here we realize that that's not really a free choice, because if we eliminate these, okay, great. Now our equation's left with only y's. But if we eliminate these, our equations have left an x and a y, which means we haven't really gained anything. We haven't made our equations any simpler because we still have both variables. So in this situation, yeah, we could work to get rid of either one, but getting rid of this one doesn't really help us. So this is the one we want to focus on. So let's go ahead and take this and multiply by -2. That way, -2 times +2 will make that a -4, and then these will be opposites. So here I'm using the addition method, which we saw in a previous section. We're now using it for a nonlinear system, but it should still work the same way. So now if I double this bottom line, I have a new system of equations. 4xy plus 3y squared equals -9. And if I multiply everything by -2 across the bottom, that's going to give me -4xy minus 2y squared plus 10. Double negative makes that a positive. And so now if I add these two lines together, that's going to give me, well, that's going to go away. 3y squared plus a -2y squared is just 1y squared. And adding these together, 10 plus a -9, well, that's just going to give me 1. So there we go. We've gotten down to a single variable. Now, we're supposed to solve for the single variable. Here we have y squared. But that's simple enough to get rid of. We can just take the square root of both sides. Now, if I take the square root of both sides, remember, when you take a square root, there's two different square roots. There's a positive and a negative. So here, this is going to give me y by itself. The square root of 1 is 1, but I want both the positive and the negative square root. So plus or minus 1. That's going to give me two different results. I'm going to get y is equal to 1 and y is equal to -1, plus or minus. You say, well, which one works? Well, that's the thing. They both do. Whenever you have a linear system of equations, we've seen that two straight lines are either, if they cross, are going to cross at a single point, or maybe they don't ever cross, they're parallel, or maybe they overlap and they share every point. But these are no longer linear systems. These are nonlinear systems. When we graph nonlinear systems, the graphs are curved, and curves might cross at more than one place. So it's possible now to have multiple solutions. We'll see that several times throughout these examples. Most of our problems will have multiple solutions. Not that they have to, but often they will. So now, if we take these, well, each one of these will provide a solution. So that means each one of these can be used to find the x value for that particular point. So now, just like with any other addition method problem, we're going to go ahead and take the value that we found, and we're simply going to plug it into one of the equations that we're working with. It doesn't matter which one we plug into. I'll use this bottom one because it has smaller numbers. That's really the only reason. So I'm going to say 2 times x times y, and I said y is the number 1, plus y squared, which is really 1 squared, is equal to negative 5. Well, 2 times x times 1 is 2x. 1 squared is 1. I could now subtract 1 from both sides here. And that'll give me 2x. These are gone. Negative 5 minus 1 is negative 6. And now if I divide on both sides by that 2, that gives me y equals negative 6 divided by 2 is negative 3. So there we go. If my y is if positive 1, my x is negative 3. So that's going to be one of my solutions. The solution to my system is going to be negative 3, comma 1. But now, here I have another possible solution. So let's go ahead and take negative 1 and plug that in. So that's going to be 2 times x times negative 1 plus negative 1 squared equals to negative 5. I'm taking this equation, and now y is equal to negative 1, which I've plugged in there and there. So this will give me 2 times x times negative 1 is negative 2x. Negative 1 squared, well, that's a positive 1, is equal to negative 5. We can now subtract 1 from both sides. And if you subtract 1 from both sides, you're now left with negative 2x. This is 0. And negative 5 minus 1 is negative 6. I can now divide both sides by negative 2. This isolates my x. And I'm left with just negative 2 divided into negative 6, which is positive 3. So now this provides another solution. X comma y. 3 comma negative 1. So there we go. The solutions to our system, it turns out for this problem, there's more than one. And here they are. These two graphs would be curves. We're not going to bother graphing them, but we could. We've seen how to graph equations. If we were to graph these, the places where these two graphs would cross, the two curves, would cross at negative 3 comma 1 and 3 comma negative 1. Now, the addition method works pretty well for this particular problem. However, you'll see that for many problems, you won't get a nice result from the addition method. So let's go ahead and consider this other equation, system of equations. Let's solve the system that is given by x squared minus 6x plus 9y squared. That should be 6xy. And that's equal to 0. The other equation is much simpler. X minus y equals to 2. Okay. Now, you'll notice that, well, there's nothing that simplifies away through the addition method. If I try to multiply things so that I get the same coefficient, well, there's nothing that matches up. Here I have an x, and here I have an x squared. But it doesn't matter what number I multiply this by, I'm still not going to make this into a quadratic. Same thing here. I can't get those to match up because that's linear and that's quadratic. It doesn't matter what number I multiply this by, it's still first power. That one needs to be second power before they could cancel out. And here this has both variables. And again, these only have a single variable. So there's no number I can multiply the x by to make it xy. And there's no number I can multiply y by to get xy. So here, the addition method doesn't really give us any result. Fortunately for us, we do have the substitution method. You'll find that when you have nonlinear systems, the substitution method works a lot more often than the addition method does. If the addition method works, it is still really much simpler than other methods can be. But if it doesn't work, well, then we have to use the substitution method. All right, so let's go ahead and take a look at how this is going to work. So with our substitution method, remember you want to pick one equation and solve for one of its variables. You can pick either equation and solve for either variable, but be nice to yourself. Here I notice I have a big complicated looking quadratic equation and here a small simple linear equation. I'm probably going to have an easier time working with this one. So I'm going to pick one equation and solve for one of its variables. Okay, let me go ahead and pick this equation here, x minus y equals to 2. And now let me solve for one of its variables. It looks like x is almost already by itself anyway. I just need to get rid of that minus y. Okay, so let's add y to both sides. That's gone. And I'm left with x by itself is equal to y plus 2. This is our substitution. So now you're going to take any instance of x in the remaining equation and replace it with y plus 2. So this is now going to become, remember, you have to use the equation you haven't used yet. You're going to have x squared minus 6 times x times y plus 9y squared. That's that top equation. But now anywhere there's an x, I'm going to go ahead and plug in my substitution. Instead of saying x squared, this is now y plus 2 squared. Instead of minus 6 times x, this is now minus 6 times y plus 2. And you'll notice that in spite of the fact that this equation is now a lot bigger, I've now only got one variable. And since I only have one variable, I know how to solve using techniques that I've learned in chapters 1, 2, and 3. All right, so let's go ahead and simplify this. Before we start solving, this can be squared out. All right, so let me go and do that off to the side. Y plus 2 squared means y plus 2 times y plus 2, which is y squared plus 2y plus another 2y plus 4. I've distributed. And if I combine my like terms, my y squared stays put, 2y plus 2y is 4y, and then the number 4 stays there. So here, this expands out to give me y squared plus 4y plus 4. Here, I can go ahead and distribute this. I have a negative 6 times y. Well, here, let me do this off to the side here. I have negative 6 times y plus 2 times y. These are all being multiplied, so it doesn't matter what order they're in. So let me rewrite this as negative 6y times y plus 2. So let me put this y over here with the 6. And now I can distribute it all together. Negative 2y times my y, well, that gives me negative 6y squared. And if I take negative 6y times my 2, well, that's going to give me negative 12y squared. So that gives me negative 6y squared minus 12y squared. Just like that. And finally, that plus 9y is that plus 9y squared. Like that. So this became this, and this stuff became this stuff. You'll notice that you have a few like terms to combine. Oh, my apologies. There should be no square on this one. Negative 6y times 2 is just negative 12y. No square on that one. Okay. You'll notice now you have a few like terms you can combine. I have some squares. Y squared minus 6y squared. Oh, well, that's going to be negative 5y squared. I got that. Here I have, and I have another 9y squared over here. So that's going to be 9y squared minus 6y squared, that's 3y squared, plus another y squared, that's 4y squared. So I'm combining my like terms. That one, and that one. I have a couple of linear terms. Hey, look, negative 12y plus 4y. Well, that's negative 8y. And then I have a single constant. That's just the number 4. So I can write that as the number 4 is equal to 0. All right. So now I can go ahead and solve that equation. Here, I notice that I can divide everything out by 4. Every one of these numbers is divisible by 4, including the number 0. So let me divide by 4. And that's going to give me 1y squared minus 2y plus 1. And here that's still equal to 0. And that can be factored as y minus 1 quantity squared is equal to 0. I could take the square root of both sides here. And the nice thing about the square root of 0 is that that plus or minus doesn't make a difference. right? Plus or minus 0 is still 0. So here, I just have y minus 1 is equal to 0, right? Plus or minus doesn't really matter here because 0 plus or minus 0, well, that's still 0. So here, I'm left with y minus 1 equals 0. And finally, I can add my 1 to both sides, and I get a result. Y is equal to 1. All right, very nice. So now, once I have that, it takes a lot of work to get here. But once you get this one, the other variable is easy because you're going to take your substitution. So now take your substitution. Let's write it down right here. Y is plus 2. That's going to equal to x. And now we know that y is equal to 1, so let's plug that in. So that's going to give me x is equal to 1 plus 2, which will give me 3. And there we go. That is my solution. It turns out that in spite of the fact that this is not a linear system, here this does only cross one time. All right? So here we have one solution is going to be 3, 1. So note, nonlinear systems might have 2 or 3 or 4 solutions, but they might just have 1. It depends on the problem. Let's take a look at another example of this. So example, let's go ahead and solve the system. And here we're going to take x minus 10 quantity squared plus y quantity squared equals 100. And my other equation in my system will be x equals y squared. Okay? Now this one could be done with elimination, because if you notice here, these two match up. They're both y squares, which means if I treated them carefully, I could get them to go away, and all that would be left would be just my x variables. The other thing we could do is we could use substitution. Here, this x is already solved for. X equals to y squared. So anywhere I see an x, I could substitute a y squared. Here, go ahead and pause the video and give it a try. Pick whichever method you like, and whenever you're ready, you can come back and we'll go through it together. I will be using the substitution method, but use whichever one you feel comfortable with. This one will work both ways, and no matter which way you choose, we should all get the same answer. All right, so let's take a look here. As I mentioned, I'll be using substitution. Elimination would work for, addition method would work for this one, but the substitution method, it's already nicely set up. So here we go. First of all, that's already our substitution. No extra work needed. All right, x equals to y squared. So now let me take my remaining equation, the one that I haven't used for anything yet, and I'm going to, everywhere I see an x, I'm going to plug in a y squared. So this is going to be y squared minus 10, quantity squared, plus another y squared equals to 100. Right? Here, that x got replaced with a y squared. That x got replaced with a y squared. Minus 10 squared plus y squared equals to 100. Everything else remained the same. So now, let me go ahead and simplify. I can square this. And in fact, let's go ahead and do this off to the side. We can take y squared minus 10 squared, which is the same as saying y squared minus 10 times y squared minus 10. That's going to be y to the 4th power. Then it's going to be minus 10y squared. That's going to be another minus 10y squared. And double negative makes that plus 100. And so that's going to be y to the 4th. Minus 10y squared minus another 10y squared is minus 20y squared plus 100. So that's what you get when you square that out. Y to the 4th minus 20y squared plus 100 plus another y squared equals 100. So this becomes that, and those two remain the same. Notice I can combine some like terms. Negative 20y squared plus y squared is negative 19y squared. Negative 20 plus 1. Plus 100 equals 100. Now, whenever you're solving a polynomial equation, that's what this is a 4th degree polynomial equation. We want to make sure one side is equal to 0, and here that works out really, really nicely, because although we were trying to make this go away, we also end up having this go away. So now we end up with y to the fourth minus 19y squared is equal to 0. We can solve this now. First of all, that has a common factor. Both of these can be divided by y squared. So I can factor out y squared to give me y squared minus 19 equals to 0. I can now solve each of these on their own. I can say, well, let's see, y squared is equal to 0. Or separately, I can say y squared minus 19 is equal to 0. If y squared is equal to 0, well, then that's just going to be y equals to 0. Yeah, I could take the square root of both sides, plus and minus. But of course, plus and minus 0 is still just 0. So I get y equals to 0. Over here, I can extract the square. Let me add 19 to both sides. That makes that go away. And this will give me y squared equals to 19. I can now take the square root of both sides, plus or minus. I have two square roots that I can take. And so now I have y is equal to positive root 19, but also y is equal to negative root 19. After all, that's what plus or minus means. It means positive or negative. So it turns out I have 1, 2, 3 different possible solutions. So my solutions, I'm going to have 3 of them. I'm going to have something comma 0. I'm going to have something comma square root of 19. And I'm going to have something square root of negative square root of 19. All right, those are all the y values of my solutions. Now to get the x values of my solutions, all I have to do is go back to my substitution. So here, if y is equal to 0, that means x is equal to, here, these are all using my substitutions. Here, I can say x is equal to 0 squared, which is just 0. Here, I can say x is equal to square root of 19 squared, which is just 19. And over here, I can say x is equal to, take your y, negative square root of 19 squared. Here, squaring a negative makes it a positive anyway, so we still end up with 19. So if my y is 0, my x is 0. If my y is square root of 19, my x is 19. And if my y is square root of negative 19, my x is still 19. Just like that. So these 3 are our solutions. So now here, let's take something a little different. Normally I would sketch these by hand, but since sketching is not something that's required for this section, and since I have such a nice pretty picture here, this will give you an idea as to what it is that physically we're looking at. We have 2 equations. One of them is x minus 10 squared plus y squared equals to 100. You may recognize that from chapter 2 as being the equation of a circle. And in fact, here it is. Here's a circle that's been mapped out. Now, x equals y squared. That kind of looks like y equals x squared, yeah? Except the variables are flipped. So it's parabolic in nature, but instead of having a y as a function of x, here we have x as a function of y. What that looks like is a parabola that's on its side. So here, if you have these 2 equations, notice that they are very different, but they do cross a few different places. Here, well, that would be 0, 0. That would be 19 square root of negative 19. And that would be 19 square root of positive 19. So here, this graph confirms what we saw in our solutions. We have 3 different solutions, which are 0, 0, 19, comma, square root of 19, and 19, comma, square root of negative 19. And in the interest of full disclosure, I am very new to this whole video lecturing thing. That shot that you saw me do, switching back and forth to the graph and back to here, that took me 10 minutes to set up, just so y'all know. Your professor might be well experienced in math, but computers, well, I know how to check my email and maybe 1 or 2 other things. So in any event, Let's take a look at one last example here. This section is a little bit short because, after all, we have covered most of the topics in a previous section where we first introduced addition and substitution methods. Here, let's just take a look at one last example. We're going to solve our system. And here I'm going to leave this as a surprise as to what exactly we're looking for. This won't look any different from any other kind of equation. In fact, it'll look very similar to the one we just saw. Because, of course, oftentimes when you're working these problems, you won't know ahead of time what's supposed to happen. So here we have a nice example of, well, we don't need to know what's going to happen ahead of time. We'll find it. Here we're going to go ahead and use the substitution method. All right, well, that's already y equals to something. So let me just use that. So let me treat that as my substitution. If you don't already have one of your variables isolated, it doesn't take a lot of effort to isolate one. Let's call this our substitution. So now we take that top equation and we plug in the substitution. So that's going to be x plus 2 quantity squared plus, and now instead of saying y squared, we're going to replace the y with 2x minus 4. Don't forget the y is being squared, so the 2x minus 4 should also be squared. Now, we're going to go and square everything out here. X plus 2 squared, well, that's x plus 2 times x plus 2. So that'll give us x squared plus 4x plus 4. And here, this will give us 4x squared minus 16x plus 16. And that's all equal to 9. So this is that, and this is that one. Okay? I probably should have done this at the beginning of the problem, but go ahead and take a minute, pause the video, and see if you can finish this off. See what happens. Once you've gotten to a place where you have an answer, go ahead and unpause the video and we can go through it together. All right, so let's see here. We have, picking up where we left off, we have a couple of like terms that we can combine. So we have 4x squared plus another x squared, and that's going to give me 5x squared. And here I have negative 16x, but then I have plus 4x, so that'll give me negative 12x. And then here I have 16 and 4 will give me 20. And that's equal to 9. Just like that. And now, since that's a polynomial equation, let me go ahead and subtract 9 over to this side so that I can get one side equal to 0 and make things a lot nicer to solve. So that's going to now be, oh, let's see, that's 5x squared minus 12x plus 11 is equal to 0. So we're left with a quadratic equation. Okay, well, we can solve a quadratic equation either by traditional factoring. I don't like the looks of those numbers. That doesn't look like it can factor out nicely. We could use the completing the square method, or we could use the quadratic formula. It really doesn't matter which one we use here. We're going to find a solution anyway. But I've learned over the years that my students tend to prefer the quadratic formula if they can get away with it, right? So here, let's go ahead and do that. Let's use our quadratic formula. The solutions to this are going to be x is equal to negative b plus or minus the square root of b squared minus 4 times a times c. And then all of this, not just the square root, but the whole thing, gets divided by double the value of a. So now let's simplify here. Double negative makes that a positive. That's positive 12, plus or minus the square root of, let's see, negative 12 squared, that's positive 144, minus 4 times 5 is 20, and 20 times 11, that's going to be 220. And then, of course, our denominator, 2 times 5 will give us 10. But the thing of interest, notice, is if you subtract those, you get a negative. In particular, you get negative 76. So 12 plus or minus the square root of negative 76 over 10. But notice, that's the square root of a negative. This would be a complex number. So what does that mean for our equations? That means that this doesn't have any solutions. Remember, our equations are, when we look at our system of equations, what we're looking for is a point on the graph where the two graphs cross. But remember, whenever we graph a function of two variables, x and y, we're graphing on the xy plane. And the xy plane has a place for you to put positive x values, and it has a place for you to put negative x values. And it has a place for you to put positive y values, and it has a place for you to put negative y values. But it doesn't have anywhere to put imaginary x values. So here, even though this equation has a solution, it's a solution that's complex. And because it's complex, it doesn't fit anywhere in our graph. But since what we're looking for is the place on the graph where these intersect, then that means that this has no solutions. So this system has no solutions. We saw that in a previous section. Whenever you have a system with no solutions, this is called an inconsistent system. And here we see the image of what we've just graphed. We had x plus 2 quantity squared plus y squared equals to 9. And that you'll recognize as being the equation of a circle. We also had the equation y equals 2x minus 4. And you'll recognize that as being a linear equation, a straight line. And by looking at these graphs, you can tell that, well, they definitely don't cross anywhere. So that does confirm what we see over here computationally, and that's to say that the system has no solutions. There is no place where it crosses. All right? So that's it for the section, and I hope you all have a nice day.